Alright, let's finish with a couple of example problems. You can see how we'll use these equations we've learned. So the first problem involves glass, so a submarine window. We've got our three materials, and a lot of times the way I'll make a drawing like this is we'll just kind of consider a close-up of the materials. So perhaps this is the layer of water up here. Then between these two lines is glass, and then down here I've got the inside of the submarine represented by air. I've got the index of refraction of water is 1.33. Glass is given to be 1.52. And then air is, for all intents and purposes, 1, just like a vacuum. We have the light beginning in the water and striking at 60 degrees to the normal. So I'm going to draw my normal line right here. The light comes in and it hits this boundary. This angle right here is 60 degrees. And I have to find the directions of the reflected rays and the refracted rays. So first of all, the law of reflection is pretty straightforward, right? Some of that light is just going to strike and it's going to bounce off, and I don't want to just write theta sub r because that might be confusing whether I'm talking about reflection or refraction. So for reflection, if you hit a surface at 60 degrees, you're going to bounce off at 60 degrees. So there's my law of reflection. Here we're going from water to glass. So this is water in this case is my pavement and glass is my mud. It's the slower material. So that bottom wheel is going to hit and stick. It's going to bend towards the normal like this. And I'm looking now for this angle of refraction away from my normal line here. So here's where I'll use Snell's law. My first material is water. So I've got N for water times sine theta for water is equal to N for glass sine theta for glass. And so I put in 1.33 sine of 60 degrees, my angle of incidence. Water 1.52 sine of theta for glass. This is my refracted angle, and solve it for theta for glass. I find my angle of refraction. Make sure your calculator is in degree mode, not radian mode. If I do that right, I get 49.3 degrees. So it comes in at a 49.3 degree angle. The final part of this problem asks me what's the angle of refraction as the light passes into the air inside the submarine. So what's going to happen is this ray is going to come down, it's going to strike this boundary here, not at a 60 degree angle, but notice we've got a little geometry here. We get the same angle, an opposite interior angle, that these two angles here are going to be the same. So what I can do is now apply Snell's law again, and now say I've got in glass, theta sub glass, sine theta sub glass is equal to in air sine theta sub air. And we can apply Snell's law again. I can put 1.52 in for glass, and it's going to strike that boundary sine 49.3 degrees. Then we get to air, which has an index of 1, sine theta sub a, and I can go solve for this. However, when I try to plug this into my calculator, the calculator doesn't give me an answer. It says it's undefined. So something strange is going on here, and sometimes when you go from mud to pavement, the light actually can't escape, and that's what ends up happening here, and this is something we'll talk about a little more next time. Okay? So if you're curious about that, just hang in there. The last question here, we've got some red laser light from a helium neon laser. We know what its wavelength is in air, so this is a wavelength, it's a distance in nanometers. But then in the aqueous humor of your eyeball, draw your eyeball here, okay? The light travels from one into the next, and then the wavelength is going to change. It looks like it's going to get shorter as it goes into this, and we're asked to find the index of refraction of the aqueous humor. So in air, the index is basically the same as a vacuum, and here we're trying to find the index in the new material. So that's related to the size of the wavelengths. So little n is equal to the ratio of lambda sub vacuum to lambda of the material, and these things are both given to me. So air, which is close to a vacuum, has a wavelength of 633 nanometers. And then I have 474 nanometers. And I know nano is 10 to the negative ninth, but I got nanometers and nanometers, so it's just the ratio of these two things. The nano cancels out, and I get 1.34. So remember, water is 1.33, so the aqueous humor, the aqua and the aqueous humor is water. It's very close to the index of refraction of water, 1.34. For the second part of the problem, we're trying to find the speed of light in your eye. So how fast is light going to travel? So the speed of light in your eye is also related to the index of refraction. So n is equal to the ratio of c to v. So now that we know n is 1.34, we can plug that in. The speed of light in a vacuum, 3 times 10 to the 8th. And we can solve for little v, and we'll get our slightly slower speed of 2.2 times 10 to the 8 meters per second. So light goes a little slower in your eye than it does in the air. And then the last piece, we're asked to find the frequency of light in our eye. And here's that good old wave equation. Oops, coming off the screen here. That we've seen so many times. Speed is equal to frequency times wavelength. And so we just got to be careful because I got different speeds and wavelengths in the different materials. I need to either pick air or I need to pick aqueous humor for either of these two. The frequency will be the same in either. So I'll just pick the aqueous humor. So I've got 2.2 times 10 to the 8th meters per second as the speed. And the wavelength and the aqueous humor was my 474 nanometers. Nano is billionths, 10 to the negative 9th meters. And we can solve this for frequency. Kind of running out of room, so my answer ends up being 4.73 times 10 to the 14 hertz. And light waves tend to have pretty high frequencies, particularly visible light. So hopefully that makes sense. Please include any questions you have and bring your questions to class as well. We'll see you next time.